Okay, now start sharing the screen. Okay, so welcome everyone to lecture 5. Today's title is Joint Probability, Independence and Bernoulli Trials. Okay. So the joint probability is a term which we use for probabilities of events which are overlapping in the sample space. So that is just a small left out topic. So I just want to include that. And then the major discussion for today will be independence and Bernoulli trials. Okay, so we'll see what is the property of independence and what are Bernoulli trials. Okay, so these are important class of practical models, right? Okay, so we'll see the outline of today's session. So today's session will be discussing about joint probability, and then we'll be discussing about independence, the concept of independence between two events, and then we extend that concept to independence of multiple events. And then finally, we will discuss what is known as Bernoulli trials. Okay, so the Bernoulli trial is it's a type of combined experiment which uses the concepts of independence. Okay, so these are the topics we are going to see today. So first, we'll see what is joint probability. Okay. So the concept of joint probability is defined for any two events which intersect in the sample space. Okay. So it is shown a Venn diagram where there are two events A and B which are intersecting, and the intersecting portion is shaded in green, right? So the probability of the green shaded region, that is what is known as the joint probability of A and B. Okay. So it is also denoted by P of A intersection B. Okay. So the previously seen A intersection B events are like the probability of occurrence of the sequence of events. Okay. So now what we are seeing here, it is the probability of occurrence of two events defined simultaneously in a sample space. So P of A intersection B. So that is the joint probability of A and B. Okay, so that is defined as P of A intersection B is P of A plus P of B minus P of A union B. Okay, so this proof is that can be directly obtained from the Venn diagram. Okay, so this is just a simple proof. It's a trivial proof. So you can yourself prove the by the use of Venn diagram. You can prove that P of A intersection B is equal to P of A plus P of B minus P of A union. Okay, we can start with the probability of A union B. Okay, so we can add the probability of A, probability of B, and then subtract the intersecting region which occurs twice. Okay, so that is subtracted. So using that equation, we can arrive at this definition of P of A intersection B. Okay, so we'll see a small example to understand what is joint probability. Okay, so it's a very simple example where we are having some 100 resistors. Okay, there are 100 resistors inside a box which have a particular type of characteristics, and the total number of resistors in each characteristics are given. Okay, so we have resistors with 5% tolerance. We have some resistors with 10% tolerance. Okay, so and then we have three different ohms of resistor, like three different values of resistors. One group is of 22 ohms, other group is of 47 ohms, and other group is of 100 ohms. Okay, so in 22 ohms resistor, we have 10 numbers of 5% tolerance and 14 numbers of 10% tolerant resistors. Okay, so the rightmost column and the bottommost row shows the total numbers. Okay, so this is an information about a box containing resistors. Okay, so now we are interested, we are creating a random experiment where a particular resistor is chosen at random. Okay, so each resistor being equally likely to get selected. Okay, and we define three events in this experiment. the event A is draw a 47 ohms resistor. Event B is drawing a resistor with 5% tolerance. And then I'm defining another event C, which is drawing a 100 ohms resistor. Okay, so using this, I want to calculate some probabilities out of this sample space. So we have an experiment, we have a sample space, and then we have defined 3 events. Now I want to assign probabilities for these 3 events. Okay, so actually I have assigned the probability for each of these resistors. Okay, so each of the resistor being equally likely. Okay, so then that is the probability that is assigned to each of these resistors. Now, so out of this, we have to find the probability of the event A. Okay, so what is the probability of event A? Drawing a 47 ohm resistor. So totally there are 100 resistors. Out of that, 44 are of 47 ohms, right? Just use my highlighter. So out of the 100 resistor, we have total 44 is of 47 ohms, right? So the P of A will be
0.44.
yeah 0.44, yeah, 44 by 100. So similarly, P of B will be B is the event, draw a resistor with 5% tolerance. So the total number of 5% tolerance resistors is 62.
0.62.
Yeah, 0.62. P of B is 0.62. And then similarly, C, draw a 100 ohm resistor. So total number of 100 ohm resistors are 0.32. Yeah. So it's 32 by 100. So these are the normal properties. Now we come to just I will just so whatever we discussed, I have just given us in terms of numbers. So now the probability of A intersection B, that is the joint probability of drawing a 47 ohm resistance as well as a 5% resistor. Okay, so a 47 ohm resistor which is having 5% tolerance. Okay, so that number is actually this column. Okay, 28. So the total number of resistors satisfying both the things, like they are the 28 is the common number in both this column as well as this row. Okay, so the probability is 28 by 100. Okay, so similarly, what is the probability of A intersection C? That is drawing. Yeah, it's 0. Yeah, 47 ohm and 100 ohm do not overlap, so both are mutually exclusive. So we have probability of A intersection C is 0. Now what is probability of B intersection C? Where 100 ohm resistor with a 5% tolerance.
0.25.
24 by 60.
So it is 24 by 100. So because we have 24 resistance of 100 ohms having 5% tolerance out of 100. So it is 24 by 100. Okay, so this is a simple example to illustrate what is joint probability. Okay, so this is just a term which is used in describing the probability of events which overlap in the sample space. Okay, so now we move on to the important concept of today, that is independence. Okay, so before we before we know what is independence, before we define what is independence, we'll just have a small example problem which in which we use all the skills that are developed in studying about the Bayes rule, right? Okay, so so this is an experiment. It's again a coin tossing experiment which is modeled using conditional probabilities, right? So I have shown the tree branches. Okay, so it is a coin toss, so it can result in a head or a tail. So the upper, assume the upper branch of the tree is the head. So assume that this is the head and this is the tail branch, and then again we are getting a head. Again, this is a tail. Okay, so similarly we are having another head and a tail. So similarly all the branches. Okay, it can go through all the branches. Right. So yeah. So in this experiment, assume that this is a conditional probability model, and the probabilities are shown here, right? So the probability of the corresponding branches are shown along with the branches. So actually, the probability is given in terms of a variable p. Okay, so what does these branches mean? So the first branch is getting a probability of head in the first trial. right? So P of H1 denotes probability of getting a head in the first trial. P of H2 given H1, that should be the actual probability of the second branch. That is probability of getting heads in the second trial, given there is a head in the first trial. So this branch similarly represents probability of getting head in the third trial, given that the first, sorry, this is a mistake here. So first and the second trial, this H1 comma H2. Okay, so given that the first and the second trials resulted in a head. So just change this so that confusion is avoided. This is H2. So similarly, other branches. Okay, so this branch has this branch describes probability of getting heads in the second trial, given that the first trial resulted in a tail. So yeah, so we want to ask three questions. What is the probability of getting tail, head, and tail? Okay, so what is the probability of getting tail, head, and a tail? So which is yeah. So I have listed, I have given the probability along with the path. So that is P and 1 minus P, P for head and 1 minus P for tails. Okay. So just this. Okay. So this THT is this event, right? That is this event. Okay. So this event occurs through along this path, then along this path, and then along this path. So we have to multiply, right? So we saw the multiplication rule. So it is 1 minus P times 1 minus P. Okay, so it is nothing but P into 1 minus P square. Okay. So now I ask another question, which is probability of getting one head.
P.
Is it P? Just think once again. So probability of getting one head. So in how many ways we can get exactly one head?
3 ways.
Yeah,
3P
so we
into
can
1
identify
minus
from the sequence at the end. We can identify different leaves. So this is one particular case where we have exactly one head. So this is again one more case, we have exactly one head, and then this particular case. Right. So what we have to do to find probability of exactly one head? We have to add the probabilities along this path and along this path and along this path. Right. So if you observe carefully, the probabilities are P into 1 minus P whole square, right? So how many?
3 into 1 minus P whole square.
Yeah, so it is 3 times of P into 1 minus P whole square. So it is nothing but 3 times of P into 1 minus P whole square. Okay, so now we want to ask the question, what is the probability of getting head in the first toss given exactly one head occurred?
3 into 1 minus P whole square.
Yes? Is it 3 into 1 minus P whole square? Just
Yes, sir.
P square into 1 minus P.
P square into 1 minus P. No, not exactly. So, okay. So to attempt this question, so first we'll use the definition of conditional probability, right?
1 by 3.
Yeah. Yes, somebody told the answer.
1 by 3.
1 by 3. Yeah, very good. So the answer is 1 by 3. So we can arrive at this answer just by using our intuition, right? So we have said that exactly one head occurred, right? We want the probability of the first toss being head. Okay, so exactly one head occurring has only 3 different possibilities, right? So it can be HTT or THT or TTH. Okay, so 3 different possibilities are there. So our favorable case is only the first possibility, that is HTT. So you can use our definition of probability by using the ratio of favorable number of events divided by total number of events. So that gives you 1 by 3. Okay, so that we are getting by intuition. Okay, so but I'm now going to use the definition of conditional probability to get the same answer. Okay, so probability of first toss heads and one head. Okay, so that is the numerator. That is the intersection of getting the first toss head and one head occurring, divided by probability of exactly one head. Okay, so probability of getting head in the first toss, so that is P of HTT divided by P of one head. Okay. So what is P of HTT? So what is the probability of getting this path? Okay, getting to this path is again P into 1 minus P whole square. Okay, so this is HTT, that is the probability along this path, that is the numerator, and the denominator is probability of getting exactly one head. So that is we have already calculated as 3 into P 3 times P into 1 minus P whole square. Okay, so we use the previously calculated results and we arrive at the result 1 by 3. Okay, so this is a particular example where the probability of the subsequent branches are not different, right? So if you see, this probability, that is P of H2 given H1, P of H2 given T1. Okay, so it doesn't change. Here also the probability is P, and here also the probability is P. Okay, so similarly P of T2 given H1 and P of T2 given T2 given T1. Okay, so this branch, so they also don't change. Okay, so these are examples of this particular experiment is an example of an experiment which has independent events. That is, what do we mean by independence is, so suppose we separate this as trial 1. Okay, so on these group as trial 2. So the probability of particular event in trial 2 does not depend on particular event occurring in trial 1. Okay, so this is say trial 1, so this is trial 2, so these are trial 3. Okay, so these trials are not dependent on each other, right? So here there is no relationship between this trial and this trial. Okay, so if these two events are not dependent, okay, so that is given by the conditional probability being equal. Okay, so whenever a situation occurs where the conditional probability is not at all affected by occurrence of a particular event, okay, so then we call those two events are independent. Okay, so we'll see it in more detail. So this is just to give a small illustration of what is independence. So we'll move on to the next slide so that we can define what is independence. Okay, so in this experiment, the occurrence of head or tail in the second trial does not depend on the occurrence of head or tail in the first trial. Okay, so that is why we call them independent. Okay, so now we'll go to a formal definition of independence. Okay. From the previous example, we can give an intuitive definition of independence. Okay, so that is P of B given A if it is equal to P of B. That is, occurrence of an event A does not provide any information about the occurrence of another event B. Okay, so then those two events are called independent events. Okay, so even if there is a conditioning event A, our initial beliefs about a particular event B does not change. Okay, so that is what is known as the independence characteristics. Okay, so P of B given A, if it is always equal to P of B, then we say it is an both the events are independent of each other. Okay, so this is an intuitive definition which we have got from our definition of conditional probability. But this definition has some limitations, right? So this definition applies only in the case where P of B is not equal to 0, right? So that is what we have seen in the previous classes where we defined conditional probability. So since conditional probability itself is defined only for the case of P of B not equal to 0, so this definition does not apply in all the cases. That is, the cases which include P of B equal to 0. Okay, so we go for another definition, which is the proper mathematical definition of independence. Okay, so which is again a consequence of this intuitive definition. Okay, so just recall that previously by the use of conditional probability, we had P of A intersection B can be written as the product of P of A and the conditional probability of B given A. Okay, so using that, so since now we have by our intuition P of B given A is also equal to P of B, we can arrive at this definition. So we just replace this conditional probability P of B given A by P of B here. Okay, so this definition is actually a consequence of this intuitive definition, but the advantage of defining independence by this method is that it applies even if the conditioning event or any event in between, any event among the two events is having a zero probability. Right, so this also implies P of A given B is equal to P of A. Right, so this is the mathematical definition of, this is a very proper mathematical definition of independence. Okay, so this definition will take it as a mathematical definition of independence. That is, if the joint probability of two events is obtained by the product of the individual event probabilities, then we say those two events are independent events. Okay, so this is the proper mathematical definition of independence, which is a consequence of this intuitive definition. Okay, so this intuitive definition is applied in the conditional probability case, and then using that we obtain this definition. Okay. Okay, so by independence, what we mean is the joint, by the independence of two events. Okay, so now we are discussing about independence of two events. Okay, so when we go for multiple events, it has a different definition. We'll look into that also. So for now, what we have defined is we have just defined what is the independence of two events. Okay, so if the joint probability of the events are nothing but the product of individual probabilities of those events, we say those two events are independent. Okay, so now there are some subtle points in this concept of independence. Yeah. So now consider this Venn diagram. Okay, now I ask the question. So here you can see two events A and B. Okay, so they are separate, right? They are disjoint events. So now I ask the question: are these two events independent? Are they independent?
Yes.
Okay, so we'll see in a little while. So being disjoint in the sample space does not imply that these two events are independent. Okay, so why? Because so by disjoint, what we mean is they don't overlap in the sample space. Okay, so suppose I ask a question. Okay, so okay, basically what we mean by independence is the occurrence of one event does not affect the probability of the other event, right? So it does not affect our initial beliefs about the occurrence of other event. Okay, so that is what we have defined here. Okay, so that is what we started for defining our independence, right? So just observe this carefully. So the occurrence of the event B does not affect your belief, sorry, the occurrence of the event A does not alter your beliefs about the occurrence of the event B, right? So that is what is the basic intuition behind independence, right? So occurrence of a particular event A does not affect your beliefs about the occurrence of the particular event B, right? So now consider this sample space. So consider this sample space, right? So suppose if I say, so event A has occurred. So initially you have some belief about the probability of the event A and probability of event B. Okay. So assume that, okay, just so assume that this event has a probability of say 1 by 3. Okay, and assume that this event has a probability of say again 1 by 3. Okay, so other events in the sample space, assume that they also have 1 by 3 probability. So I'm giving this 1 by 3 for collection of all other any possible events in the sample space. Okay, Okay, so A has a probability 1 by 3, B has a probability 1 by 3, and the other events out there in the sample space, they have collectively they have probability 1 by 3. Okay, so now if I say if I give a partial outcome of this experiment and I say that event A has occurred, right? So I am saying that event A has occurred, right? So what is the probability of the event B occurring now? You are able to identify? Yes?
1 by 3.
Is it 1 by 3? See, I have said that event A has occurred, right? So that is the partial outcome I have observed of the experiment. So now what is the probability of event B?
0.
0,
Sir.
right? So the probability of event B, our initial belief is that the probability of event B is 1 by 3. But now since I have given this condition, okay, that is A has occurred. So this term 1 by 3, it has drastically changed to 0, right? So occurrence of an event A has drastically changed my belief about the probability of event B from 1 by 3 to 0. Okay, so that means these two events are not independent, right? So these two events are not independent. So are you able to understand the concept? So only thing we know is these two events are disjoint. Okay, so being disjoint doesn't mean that they are independent. Okay, so being disjoint is a case of extreme dependence. Okay, so those two events are extremely dependent on each other. So occurrence of one event completely eliminates the possibility of the occurrence of other event. Okay, so this is called extreme dependence. Okay, so any two events which are disjoint in the sample space, they are extremely dependent on each other. Okay, so that is that is a fine point you should understand about being independent. Okay, so okay, so disjoint events are we can also call them as mutually exclusive events. So the important point to observe here is mutually exclusive events cannot be independent. Okay, so why they cannot be independent? You can just observe this definition of uh, independence. Okay, so what do mutually exclusive events have for this parameter, that is P of A intersection B? So if these two events are mutually exclusive, P of A intersection B is 0,
0.
right? Yeah. So if those but if you can see here that P of A is having a non-zero value and P of B is having again a non-zero value of 1 by 3, right? So this is P of A and this is P of B. Okay, so we cannot obtain a zero value by multiplying two non-zero constants, right? So that is why we say mutually exclusive events cannot be independent. Okay, so this is an important point about independence and mutual exclusiveness. Okay, so if two events are mutually exclusive, they cannot be independent. In other words, mutually exclusive events will be definitely dependent on each other. So that is why we have given this extreme dependence. Okay. Okay, so these are just fine points you should note about independence. Right. So before we move on to the next slide, I just want to take attendance. Just take a snapshot. So today there are only 55 people. Suddenly it increased to 56. Okay. This is first. Three. Some people are on and off. So just now I think they logged in. Okay. So taking snapshots. So again, we move on to our lecture. So now we move on to the definition of the independence of multiple events. Okay. So this pretty. So now we move on to independence of multiple events. Okay. So when we say multiple events, so we can again consider our initial example where we saw the multiple tosses of a coin, right? So we can say that in the initial example itself, we said that each toss is independent, right? So, so how do we define the independence of a collection of events? Okay. So intuitively, what we want to say is, so if we have some collection of say 6 events, okay, so the information about particular events or their combination in the sample space should not affect our beliefs about another set of events. Okay, so we just have an intuitive definition. Okay, so here I have given an intuitive definition, and then we are refining our definition to exactly represent what we want to define. Okay, so here we have defined some probability. It is a conditional probability. So this is a combination of some collection of events. Okay, again this is a combination of the collection of some other events in the same sample space. Okay, so if information about the occurrence of this combination of events does not provide anything about the occurrence of this combination of events, okay, so then we say that the events are independent. Okay, so this is a very clumsy way of defining independence, and again this is an intuitive way. So we say that probability, this conditional probability is same as the initial belief about the combination of events. Okay, so that is the intuitive definition. Okay, so now we come at a mathematical definition of independence of a collection of events. Okay, so what we say is that, so given a sample space with multitude of events like A1, A2, A3 up to AN, okay, so we call them independent only if P of AI intersection AJ intersection, so different intersection up to AQ. So we'll see what are these indices I, J and Q is equal to the product of P of AI, AJ, P of AQ, etc. for any distinct indices I, J, Q, okay, which are chosen from the set 1, 2, etc. up to n. Okay, so this is a little bit tedious definition. Okay, so we'll see what do we mean by this definition. Okay, so events A1, A2 and A3, we have defined some n events. So all these n events are independent only if any combination of the intersection of those events is nothing but a product of the individual events. Okay, so the intersection here can be it can be of any type, right? So suppose we have say 3 events. Okay, so here for illustration purpose, I have taken n equal to 3. Okay. So if we consider 3 events, so 3 events are independent only if they meet all these equations. So if they satisfy all these equations, right? So P of A1 intersection A2 intersection A3 should be the product of P of A1, A2 and A3, right? So P of A1 into P of A2 into P of A3. So it should satisfy this condition. Also, they should be independent by individual pairs, right? So P of A1 intersection A2 should also be equal to P of A1 into A2. So P of A2 intersection A3 should also be the product of their individual probabilities. Similarly, P of A1 intersection A3 should also be the product of their individual probabilities. Okay. So independence of multitude of events is defined by having all these equalities satisfied. Okay. So this all these equalities being satisfied is what is given in this definition. Okay. So we can go through the definition. So this mathematically little bit rigorous definition. So you can go through this definition. There are other forms of the same definition given in the textbook, so you can even study those definitions. So this is a little bit simplified definition compared to that given in the textbook. Okay, so this is how we define independence of multitude of events. So compared to independence of two events where we have only a single equation, right? So P of A intersection B is the product of P of A and P of B. So when you have multiple events, so we have 4 different equations to satisfy for the case of n equal to 3. Okay, so in general, so the number of equations that n number of events have to satisfy is given by 2 power n minus 1. Okay, so the total number of equations that the event should satisfy, so you'll be seeing in a quiz problem. Okay, so now these are the conditions which all the events should satisfy to call them as independent events. So these 3 equations, the final 3 equations where we are just considering two events, so those equations are called pairwise independence relations. Okay, so we call them as pairwise independent relations. So P of A1 intersection A2, P of A2 intersection A3 and P of A1 intersection A3. So these are called, since we are considering only two events at a time, so we call them pairwise independence relations. Okay, so to have independence in a multitude of events, that is a collection of events, we should have the total independence that is given by the first equation, and also we should have pairwise independence, which is shown by the last 3 equations, last 3 relations. Okay, so now we just want to ensure that pairwise independence does not mean total independence. Okay, so for that I have taken a particular example. Okay, so consider the example of 2 tosses of a fair coin, right? So 2 independent fair coin tosses. Okay, so we have a particular example. Okay, so in that example, okay, in this experiment, we define 2 events. So event A is the first toss is H, right? So event B is second toss is H. Okay, so before that I have listed all the possible outcomes of this experiment. Okay, so what we are doing is we are tossing coins, 2 independent tosses of fair coins. Okay, so we are tossing a single coin 2 times. So one possible outcome is head in the first toss, head in the second toss. Again here, head in the first toss, tail in the second toss, tail in the first toss, head in the second toss. Similarly, both the tosses being tails. Okay, so all these are mutually exclusive. So we are assigning a probability of 1/4 to 1/4 to all of these events. Okay, so now we have defined the 2 events. Event A is first toss is H and B is second toss is H. Okay, so what are the outcomes that correspond to event A? Okay, so these are the outcomes that correspond to event A, that is first toss being heads. Okay, so what is the event corresponding to the second toss? Okay, so these are the events corresponding to the second toss being head. Okay, so now what is the probability of A individually and B individually?
1/2, 1/2.
1/2 and 1/2, right? Because so two events out of the 4 events are our favorable events, so it is 1/2. Again, P of B is also 1 by 2. Okay, now what is the product of P of A and what is the product P of A into P of B?
1 by 4.
1 by 4. So the product is 1 by 4. And then if you see the place where these two events overlap, so this is the place where these two events overlap, and you can observe that that place has a probability of 1 by 4. Okay, so this 1 by 4 is obtained by the product of P of A and P of B. Okay, so by this what we mean is A and B are independent events, right? So this particular collection is our event B. Okay, so this particular collection is our event A. So they both overlap here. So this is our A intersection B, right? So the probability of A intersection B turns out to be the product of the individual events A and B. Okay, so A and B are independent. Okay, so what we see here is they are pairwise independent. So A and B are pairwise independent. Okay. So we can verify. We have already verified independence of A and B. Okay. Now we again define. Once again we define another event C. Okay. The C event is defined as first and the second tosses give the same result. So what is this event? Where do first and second tosses give the same result? In the diagonally opposite squares, right? Yeah. So C is this event, right? So first and the second tosses give the same result. So these two are the events where we get the same result. Okay. So now what is the probability of C? Again it is 1 by 2.
1 by 2.
Now what is the probability of C intersection A? So where do these two events intersect?
1 by 4.
1 by 4, sir.
1 by 4. Yeah. So these two events intersect in the first square, right? So that is 1 by 4. So if you calculate P of C and P of A, again it is turning out to be 1 by 4, right? So if you calculate the product of P of C and P of A, so already we know P of A is 1 by 2. Again now we calculated P of C is 1 by 2. So P of C intersection A is 1 by 4, which can also be obtained by taking the product of P of C and P of A, right? So it is also verified that A and C are independent, right? So first we verified A and B are independent, and now we have verified A and C are also independent. Okay, so now what is the probability of A intersection B intersection C?
1 by 4.
1 by 4, because all the three events intersect in the top right square, top left square, right? So it is 1 by 4. Okay, now we have seen that the events are independent by pairwise, right? So A and B are independent, A and C are independent. Okay, so we are not verified for B and C, right? So A and B, A and C are independent pairwise. We are not verified for B and C. Okay, so anyway, that will be verifying. So now we ask the question: what is the conditional probability of C given A and B have occurred?
1.
1.
Yeah, it is 1. So given A and B have occurred, so A intersection B has occurred. So only one square overlaps. So the conditional probability is 1. Okay. So now we can see that the initial probability of P of C, it is 1 by 2. Right. So initially P of C has 1 by 2. Okay. But the occurrence of other two events A and B has changed the probability of P of C to 1. Right. So this shows that all the three events are not independent. Okay. So although they are independent by pairs, so which is verified here, A and B and P of C intersection A is 1 by 4. Okay. So although they are pairwise independent, collectively they are not independent. Okay. So collective independence is not guaranteed if the events are pairwise independent. Okay. So this is the point I want to stress using this example. Okay. So if a collection of events have to be independent, they should be both pairwise independent as well as independent when we take all the events together. Okay, so they should satisfy all the 4 equations, only then we can call them independent. So pairwise independence does not guarantee they are independent. Okay, so now we come to the concept of pairwise independence does not imply independence. So now we come to the concept of Bernoulli trials. So independence, with that we have completed the independence. So now we see what is Bernoulli trials. Okay, so Bernoulli trial is a particular random experiment model. So it applies to a large class of practical problems. Okay, so basically what Bernoulli trials are, so it is a combined experiment of n sub experiment. Okay, so what we are doing is we are doing sub experiment. So this is one experiment, this is an experiment, this is an experiment. So it is just our extension of our previous example. Okay, so we are doing multiple tosses of coin. So the same thing can be extended to define what is known as a Bernoulli trial. Okay, so it is a combined experiment of n sub experiment. So each sub experiment will have only 2 possible outcomes, which we can call them as elementary events. And one more condition is there in one more condition should be satisfied to call these trials as Bernoulli trials. That is, elementary events are statistically independent. Okay, so we are applying our previous definition of independence between 2 events to elementary events. Okay, so that is different tosses. Okay, so there are a lot of examples where you can see the application of Bernoulli. We can describe using the Bernoulli trial model. Okay, so to immediately understand what is Bernoulli trial, you can consider the example of our coin toss. Okay, so suppose we have different trials. So this is trial 1, trial 2, trial 3 up to trial n. Okay, so each trial results in either heads or tails. Okay, so the second trial also can result in a head or tail. Third trial similarly head or tail. Okay, so each path along this tree represents a sequence of trials. Okay, so that is the Bernoulli trial. Okay, so what are the conditions for being a Bernoulli trial? All the elementary events should be statistically independent. Okay, so now we denote the event on top by A, and the only possible other event is A bar. Okay, so we assume some probability P for the event A, top event A, and the opposite event has a probability of 1 minus P. Okay, so P of A is equal to P, then P of A bar equal to 1 minus P. Okay, so now a question of practical importance is, what is the probability of A occurring K times out of n trials? Okay, in Bernoulli trial, so Bernoulli trial is a random experiment model. So a question of or a result of practical importance using this model is asking the question, what is the probability of A occurring K times out of n trials?
NCK into P power K into 1 minus P whole power
very
K
good.
N
power
minus
N.
K.
Very good.
P power K.
So that is the result I want to derive. So I think you're already aware of this result. Okay, so it is like if we say A is success and A bar is failure. So we are basically asking the question, what is the probability of getting K successes out of n trials? Okay, so yeah, I've given the same thing. So since we have statistical independence, so probability of A occurring K times out of n trials is the product P of A having K times and P of A bar having n minus K terms. Okay, so this is because of our statistical independence between each trial. Okay, so now this probability result we have obtained only for a single path, right? So along the single path, so if you travel along a single path, so like this, take some single path. So we have calculated the probability along one particular path which has K successes out of n trials. So similarly, we can have say any different path. Okay, so resulting in the same K successes, right? So now we have to count all those paths. So how do we count all those paths? So we use combinatorics. Okay, so that is where we get our. Okay, so we have to add all those probabilities of each path to get our final result. Okay, so that is why we use our combination, right? So combination of that is NCK, right? So selecting k objects from n objects at a time. Okay, so that is given by n factorial by k factorial. That is combination of k out of n events or n objects. So selecting k objects from n objects. So that is the total number of such paths along the tree. Okay, so we multiply all those paths with, or the total number of such paths with the probability of an individual path, that is p power k into 1 minus p whole power n minus k. Okay, so that is our Bernoulli trial. So that is what I wanted to stress in this Bernoulli trial model. So we have a tree diagram, or we have a collection of events which is successive successes and failures. So out of that we ask the question, what is the probability of getting k successes out of n trials? Okay, so that this is the final result which you want to get for Bernoulli trial. Okay, okay. So with this I end this session. Okay, so have any doubts in the session? So what we have seen is we have seen what is joint probability. We have seen what is independence. So independence of two events, and then we defined the independence of multiple events, and then finally we saw what is a Bernoulli trial. Okay. So okay, now the number has increased to 58. So for the two people who come here. Okay, so I have taken attendance already. So only those people will be given attendance. So please be for the class for the entire session. Okay, so don't go on and off. Okay. And okay, so regarding the quizzes, so there are some 3 quizzes pending. So today night by 7 o'clock, I'll be enabling all the 3 quizzes. Okay, so we can see the can go through the lectures, say from lecture 3, 4, and 5, right? No, actually it's from lecture 2. So from lecture 2 till lecture 5. So you'll be having total, there are 4 lectures, but I have combined the lectures 3 and 4. Okay, so you'll be getting 3 quizzes. Okay, so I have shared all the PPTs in the class stream. So you can see, you can go through the PPTs and attempt the quizzes. Okay, so I'll be giving 3 quizzes tonight. Okay, so quizzes will be open from today night to until tomorrow evening, so you can attempt those quizzes. Okay, so with this I complete the session. Okay, so we'll end this session now. You can leave now. You can leave for the next class.